To understand about the directions of the magnetic field due to a current loop, in this video we shall discuss one application of this magnetic field due to a circular current carrying loop. Okay, now look at this question. The question says that a long wire having a semicircular loop of radius r, now this carries a current I as shown in this figure. So we have to find the magnetic field due to this entire loop at the center of the loop, that means at the point O. Okay, all right. So now let us solve this problem. As you can see in this figure, we have two types of conductors. One is a straight conductors like PQ and ST. So this PQ and ST, they are straight conductors. So when you join, O, right? If you draw the radius OQ in this case, then this radius OQ, which is the radius of this semicircular loop, it makes an angle how much with respect to this linear line? Answer is 0. Similarly, with respect to this ST, the angle between the radius R and this line ST is 0. So therefore, the magnetic field due to the uh, two straight arms of the semicircular loop, it will be B equal mu naught upon 4 pi I dl sine theta upon r square. But since we are saying B, it means you have to integrate this equation. Okay? Or the total magnetic field at this point O due to the two straight arm PQ and ST, it will be equals to how much? What is theta? Theta is actually the angle between the radius r and the current element, right? If you consider any current element along this arm PQ. So that current element, right, it is always directed in this way, which is along the same as the directions of r. So therefore the angle theta in this case will be 0. Similarly, if you look at the other arm ST, the angle between r and ST will be the same. So theta here is 0. So when theta is 0, then we know sine 0 is 0. So 0 into anything will be 0. So the magnetic field at a point O due to the two straight arm PQ and ST of the conductor at a point O will be 0. Okay, alright. Now, what is the magnetic field at this point O due to the semicircular loop? Will the semicircular loop contribute any magnetic field at the point O? The answer is yes. So let us see here. This is a conductor, this is the radius R. Now if you consider any element dl, right, over this length here, then you will find this angle between R and dl is 90 degree. So using against Weierstrass law, where B is equals to, right, mu naught upon 4 pi I dl sine theta upon R square. So now, before, if you remember, in Weierstrass law, we usually write dB, but here I will write B because I'm taking about, the total magnetic field at a point P due to the entire semicircular loop. So therefore, B here will becomes mu naught upon 4 pi. Okay, this is a constant quantity. I'll take outside the integration. I is constant, which is the current passing through the loop is constant. Radius of the loop is constant. So inside integrations, I'll have only dl sine theta. How much is theta in this case? In the semicircular loop, which is the angle between r and dl, it is always 90 degree. Okay. So again, B is equals to mu naught I upon 4 pi r square. What is sine 90? Sine 90 is 1. So what you will have inside integration is just dl. Okay. Now this dl, it means this small length. So when you integrate dl, that means you are going from q to s. That means you are going along the semicircle. So along the semicircle, we know the total length should be half of the circumference, which means the limit of integration in this case will be 0 up to, because we know in a circumference, right, it is 2 pi r, which is the total length of the circle. If it is just a semicircle, then this, if we divide by 2, then this factor 2 will gone, and we have just pi r. Okay. So b here is equals to mu naught I upon 4 pi r square. Now this integrations of dl, it is equals to L. And the limits of integration is from 0 to pi r. Okay. Now if we substitute the limits of integration over L here, you will get upper limit is pi r. So instead of L, we'll write pi r. And then we subtract by putting the lower limits of L, which is 0. Or b is equals to how much here? Just mu naught I upon 4 pi r square times pi r. Now this pi with this pi cancel. This small r with this r cancel. So your magnetic field at the center of the semicircular loop becomes how much? Mu naught I upon 4r. Okay, so this is the required expressions for the magnetic field at the point O due to the entire wire of the conductor. Okay, so please remember here that these two linear conductor like PQ and ST, they will not contribute any magnetic field at a point O, but the only contribution is due to the semicircular loop, which means due to semicircle. So that is why we have the magnetic field at the point O due to this semicircular loop. It is equals to mu naught I upon 4r. Okay. Alright. So if this is the expressions for the magnetic field at the center of a semicircle, then what will be the magnetic field at the center of a circular loop? When I say circular loop, mean it is a full circle. So for a full circle, right, this magnetic field, it should be twice this mu naught I upon 4r. Okay, because semicircle is just half of the circle. Here this is a semicircle, so it is half of the circle. So when I say complete circle, it means I have to multiply, this magnetic field by the number 2, because there are two semicircle in this case. One is up and another is down. So your magnetic field at the center of the circular loop now becomes 2 times 1, 2 times 2, which means mu naught I upon 2r. So this is the expressions for the magnetic field at the center of a circular loop. So for this, I think, right, we have done, right, in the previous lecture video also about how do we get this equation for the magnetic field at the center of a circular loop carrying a current I. Okay, so this is the same thing only, right? So in exams, right, when the question asks you about to derive the expression of the magnetic field at the center of a circular loop, so that means you have to obtain this equation. You can either obtain this equation using my previous lecture video, or you can use this concept here also. It's true. Okay. Now, where is the directions of this magnetic field B? Okay, looking at the circular loop, where is the directions of this electric field B? Now the current is right going in this way. So this current, right, I will imagine like these current now, they will be represented with my call fingers. So if my call fingers of my right hand stands for the directions of current, then my thumb will give the directions of the magnetic field at the center. So therefore, the magnetic field at the center of this semicircular loop, it will be pointing perpendicular to the point O, which means perpendicular to the point O, or I can say it is perpendicular to the plane of the semicircular loop. Okay. Alright, so this is all about this numerical problem.